Alright. So, alright, sadly, for real, we have today, Thursday, Friday, Monday. That's it. That is the end of our instructional time. Then we have next Tuesday, which is like the exam block, and we'll be in the gym, and we'll do all the things, and life will be good. You know what? Like, that's it. That's the end of our time together, and it really does make me sad. I'm excited about the class of 2018 and 364 days, but like, I'm gonna miss y'all. And even those people that I've actually never met on the other side of the camera, I'm gonna miss my trailblazers, I'm gonna miss my explorers, maybe even some wizards. I'm gonna miss y'all. I'm not going anywhere. You are. Okay? And you'll all be back in August, for sure, I'm sure. Okay, so here's what I know from talking to alum that have taken Calc AB and Calc BC before, especially the alum that make this decision to take Calculus 2 in the fall. Number one, if you are in Calculus BC and you have earned a qualifying score on the AP exam, which you won't know until July, Calc 2 is absolutely the right thing for you to do. It is 100% the right thing for you to do. You are ready. I know you are ready. And you have a survival guide that's going off to college with you. If you're in Calc AB, if you get a 5 on the AP exam, then I think Calc 2 is the right thing to do. If you did Calc AB and you get a 3 or a 4, take Calc 1 again. Get a good solid grade, go through that, make sure you really understand calculus deeply, especially if you have to take Calc 2. But the next 4 days, we're going to focus on things really targeting those future Calculus 2 students. These are some places where there have been some gaps in the past. So I'm doing this in a slightly different order. Mine says page 1. There's like 3 or 4 different places in your packet that says like page 1. Yeah, because
it's like the third page one.
It's like the third page one that's in there. It looks a lot like what's up here right now. Stephen, if I'm over here, can people see? Okay, so over the course of this year, we have looked at a whole bunch of derivative rules. For example, the power rule. Power rule says what?
Bring the exponent down.
Bring the power down.
If you have x to a power, like x to the 5th power, the power rule says
Bring the power
bring the power
down.
down, reduce the power by 1. And if I said find the derivative of sine of x, you guys would all tell me? Cosine of x. And if I said derivative of e to the x? E to the x, and I said derivative of arctangent of x?
1 over 1 plus.
1 over 1 plus x squared. Like, you know the derivative rules, but at the time I wasn't worried about proving them. We did some examples, we looked at some graphs, and I made it really clear every single time. These are not proofs. We're finally actually going to do some of the proofs. So for example, this first one that we're gonna look at is the product rule. You guys all know the product rule. What does the product rule say? Derivative of the first times the second plus the first
times the derivative of the second.
One more time, what does the product rule say?
The derivative of the first times the second plus the first times the derivative of the second.
Louder! The product rule says?
The derivative of the first times the second plus the first times the derivative of the second.
One more time, the product rule says?
The derivative of the first times the second plus the first times the derivative of the second.
And now in stand and deliver mode, why? Why is this the case? Maybe I have lied to you all along, and that's actually not the product rule.
Look, I think I wrote that on the test.
You're like, I wrote that, I used that, you told me it is correct. If it's wrong, it is absolutely 100% correct. But here's the thing, in order to prove something, you need to go back to basics. You need to go back to your foundations. And in your foundations is the difference quotient. Remember way back in the day when things were hopping? Oh yeah. It was back. Should have worn my little beanie. Like back in August when we first, and this is like what pre-calc students have been doing right now. They're doing things like find, for example, like if f of x equals x squared, find f prime of x. And they all just took a test on this, right? Find f prime of x, and you guys all know that f prime of x is?
2x.
2x. But what they have to do is they have to use the difference quotient, which says f prime of x is the limit as h approaches 0, f of x plus h minus f of x over h. Welcome back to August. You went to pee and you stepped into a time warp. So f of x plus h in this case means x plus h, the whole thing squared, minus f of x is x squared over h. You guys remember being there? We did this. This is where your calculus journey started. And what would we do from here? You multiply out the x plus h with x plus h, and it's not, oh god, don't tell me it's x squared plus h squared, it's not.
X squared plus h squared plus h.
It's x squared plus there's a 2xh plus h squared minus x squared all over h. Right, this is our definition of the derivative. This is applying that definition, and now we look for some fancy algebra, x squared minus x squared, those cancel. Other fancy things?
Take out an h. And then
Take out an h and cancel, so you take out an h, so that's 2x plus h over h. These guys cancel, right? Algebra. Now we get to the limit. Limit as h approaches 0 is 2x. Check. That's a proof. This is what a calculus proof looks like, feels like. This is how we do it. What we did back in the day is we said, like, let's do some examples. We did x cubed, we did x to the 4th. Stephen came into the world knowing some of these things. You were Googling in the womb, I'm sure. Our little cell phone.
a brick.
What I want to do, yeah, it was a brick, it was a big phone. I want to actually prove the product rule. And we're going to prove a couple of the derivative rules. We're going to jump around in the handout, David, it's going to be okay. Okay, I want to prove that the derivative of f of x times g of x is f prime of x times g of x plus f of x times g prime of x. Or as you guys told me, derivative of the first times the second plus first times the derivative of the second. Everybody okay? Alright, so here's the proof. A proof, you get to work on one side of the equation but not the other. Okay? So if I want to find the derivative of f of x times g of x, well, then that's going to be the limit as h approaches 0. F of x plus h, in this case, this is like the function. This is the f. I know it's a little weird because there's an f over here, but like if we go back to our derivative, it's whatever your function is, replace the x with x plus h, minus subtract the original function divided by h. In this case, it looks like f of x plus h, g of x plus h, minus f of x times g of x all over h. This is the definition of the derivative. Is everything mostly okay? Okay. Now, fancy algebra. Anybody see any? Fancy legal algebra. Only legal stuff here. Anybody tempted to distribute the f and say it's the same as f of x plus f of h? Good, because we can't ever do that, ever. Can't do that with g either. Anybody see any factoring that can be done between these two expressions? No, there is none. I want to make this a little prettier. We're going to make this limit as h approaches 0, f of x plus h times g of x plus h minus f of x times g of x plus h plus f of x times g of x plus h minus f of x times g of x all over h.
Why is that bird here?
And it's nicer. First of all, I need to know, is what I just did legal?
Well, yes. Yes.
Is it legal?
Yes.
Why is it legal?
Because it cancels. It cancels.
Right, what I did, like we had this term already, we had this term already. What I added in is all this stuff over here. Right, that didn't exist before, and that's not an obvious thing. I wouldn't expect any of you guys to just like do that. But it's legal?
Yeah.
Why?
It's the same thing.
I've got the negative of f of x g of x plus h. I've added in the positive of f of x g of x plus h. We know algebraically they're going to cancel. So what I did is I added 0. There's a reason that I added the 0. And let's look at what happens. What I added is 0, so it's legal. Check. But it has to be legal and better for this to be the right thing to do. what this allows me to do, look at just the first two terms. Anything happening there?
You can
Factor out.
You can factor out.
F of x plus h times g of x plus h minus f of x times g of x plus h. I can factor. There's a common factor now. What's the common factor?
G of x plus h.
It's the g of x plus h. What is left is f of x plus h minus f of x. Right, that was factoring out this g of x plus h from both. Let's look at the last two terms. Anything happening here?
Factor out the
You can factor it.
I can factor out f of x plus f of x, and what's left is g of x plus h minus g of x. This whole thing being divided by h. Okay? Stuff's going to start to happen quickly. One of the properties of limits is that you can distribute a limit over multiplication. You can distribute a limit over addition if you want to. There's lots of things you could do. You could also say this whole big numerator being divided by h is the same as saying this part divided by h plus that part divided by h. I hope everybody's okay with that. I'm going to distribute the limit and say that this is the limit as h approaches 0 of g of x plus h times f of x plus h minus f of x all over h plus the limit as h approaches 0 of f of x times g of x plus h minus g of x all over h. And I can go a little bit further and say that this is the same as the limit as h approaches 0 of g of x plus h times the limit as h approaches 0 of f of x plus h minus f of x all over h.
Oh my gosh.
Plus limit as h approaches 0 f of x times limit as h approaches 0 g of x plus h minus g of x all over h. It's just a lot of algebra and limit properties. Celeste, it sounds like you just had an epiphany.
The limit as the second part, or this first limit, so after that part?
This part over here.
Right here, yeah. That equals f prime of x.
The limit as h approaches 0 of f of x plus h minus f of x all over h. We know what this is. We know what this means. What is this? All of this in here that I'm going to box off in the brown is f prime of x. Anybody see anything else? It's the same thing over here. This limit as h approaches 0 of g of x plus h minus g of x all over h is g prime. Okay, so I'm going to do a little bit of bad board spacing here. So we've got the limit as h approaches 0 of g of x plus h, all that times what you guys told me was that's really f prime of x, plus the limit as h approaches 0 of f of x, this whole thing times g prime.
Limit is g.
Isn't what just g?
Limit of g of x plus h is g.
The limit of g of x plus h as h approaches 0, h gets close to 0, but x doesn't change. This is really just g of x times f prime. Limit as h approaches 0 of f of x. H is getting close to 0. It's just f of x times g prime. So using the definition of the derivative, we're able to actually go through and prove that the product rule, the derivative of a product of two functions, is found by, it showed up in a slightly different order than the way that we write it. Derivative of the first times the second one, plus the first one times the derivative of the second. This has been proved. congratulations. Some people put a little smiley face. You might have a professor that does the box at the end of a proof. It's just math notation. Some people do a little QED. They want to show off their Latin. It may be Greek, I don't know. So we have the language. QED stands for quickly and easily done.
Easy.
It actually, that's not what it stands for. It stands for quod erat demonstratum. That's Latin or Greek, right? Quod erat demonstratum, basically, like, I have shown what needed to be shown.
I'm about to go to college.
I'm also a fan of, although my real analysis professor was not happy, I would just say, ta-da. He really didn't like that. He really didn't like that. He's like, you could do the box, or you could do the QED. I'm like, what difference does it make if I say ta-da? I was like, I just did 10, like, we did 10, like, seriously, 10-page proofs of these different theorems. And I was like, I'm doing the happy dance right now, and I just want you to know how happy I am that I, like, made it through. Ta-da! Everybody good? Ta-da! Exactly. Take that, sucker. Alright, cool. That is a proof. Anything that we have done before this doesn't count as a proof. This is a proof. This is what would be expected of you in like a Calc 1 course. Alright, so let's do another one.
Calc 1.
Oh, another good one. Another good one. Oh, we're hopping. Oh, yeah.
Did you give us enough space for these?
Did I actually, and next year's class isn't going to get any space at all. To conserve on some paper, they're just going to have to like bring in a notebook. Huh? No. No, but just like really trying to be sensitive to like.
You read their homework.
Alright, so I want to prove using the definition of the derivative that derivative e to the x is e to the x. We know the derivative of e to the x is e to the x, right? So let's do a proof. So the proof starts like this. The derivative of e to the x is limit as h approaches 0, e to the x plus h minus e to the x all over h, right? I'm using this bad boy over here in this particular problem. What I need is clever algebra.
E to the x plus h. E to the x plus. I mean, what?
What about this e to the x plus h?
Yeah, this, you know. E to the power of h.
Is the same as e to the x times e to the h minus e to the x all over h. I hope we're okay with that. Any other legal fun stuff you can do here? I can factor out that e to the x. Okay, I can say this is the same as limit as h approaches 0, e to the x times e to the h minus 1 all over h. You could go a little bit further and say, well, isn't that the same as the limit as h approaches 0 of e to the x times the limit as h approaches 0 of e to the h minus 1 all over h? Is that legal? Sure. Limits have really nice properties. Limit as h approaches 0 of e to the x is e to the x, right? Because there's no h here. This is just e to the x times the limit as h approaches 0 of e to the h minus 1 over h. Now, I'm pretty sure the 10 of you know what that has to be. 1. It has to be 1. It absolutely must be 1, otherwise I've lied to you about the derivative of e to the x being e to the x. It must be 1. I need to be convinced that it is 1. Now, here's the problem with using L'Hopital. Okay. If you're in Calc 1 right now and what you're doing is proving derivative rules, you don't know what L'Hopital's rule is. And you're trying to prove that the derivative of e to the x is e to the x. You can't use L'Hopital's rule and say, oh, the derivative of e to the h must be e to the h, right? You wind up in like this circular issue. I'm trying to prove this, I can't use it. I'm trying to prove it, can't use it. L'Hopital's rule off the table. Thank you for bringing it out, though.
Right.
Anybody remember the squeeze theorem?
Oh, bro.
I remember what the picture there was.
Remember how
There is a picture. It is, you could use, an option is to use the squeeze theorem.
But that's a theorem.
That's a theorem, but if you have proven it, once you've proven it, you get to use it.
Not here.
Anybody remember how to find limits on the calculator?
There it is, calculator.
Right, you like graph this function on your calculator, and then you like let the x values or the h values get closer, closer, closer to 0, and you look for trends. Okay, you can do this on the calculator. I will tell you, probably your calculus teacher is not going to be a fan of using the calculator, so that's off the table.
You spell calculator wrong? No, I see it.
Right, I got it. Squeeze theorem, if you remember it. Calculator, if you remember it. This actually was a limit that we proved at one point. So you can do like a previously known thing. Oh, here's another thing that you can do. Taylor series expansion. You can do the power series expansion for e to the x, which is, how does that work again? E to the x.
1 plus x
It's
plus
1
squared
plus x
over 2
plus x squared over 2 factorial plus x cubed over 3 factorial. Way to go, that's way far. Way to go, young eyes. So if you replace, stay with me. If you replace e to the h with the power series expansion, 1 plus h squared over 2 factorial, h cubed over 3 factorial, subtract 1, that leading 1 cancels out. Everything left in the power series expansion is like powers of h. You could divide by h, and what would survive is 1. So power series expansion is another way. Power series expansion is another way. Either way, it would be okay that this is going to have to be 1. And then we'd say e to the x, and then we'd say, ta-da! Don't try that in college, you're going to get in trouble. Or the box, or QED, or any of the things. Quod erat demonstratum. Maybe keying at the time, I'm not sure. Okay, but here's the thing. These are proofs. They require the use of the definition of the derivative, not fancy schmancy power rule stuff. You're proving the things. This is the way that we go. All right, I want to do one more. We're going to jump ahead to, it is on page number 4. Example number 9. I want to find the derivative of x to the x. And I'm going to assume that we've proven all the things that need to be proved prior to this. We're not actually going to use the definition of the derivative. Check this out. This used to be a calculus BC topic. It's not anymore.
What is it now?
Like Calc 2 or Calc 3.
Okay.
Okay.
Oh, this one is last space.
What are the thoughts here? Power rule? Power rule works for extra power. Do we have extra power? Yes, but the power rule works for x raised to a constant power, like x to the 5th, x to the 10th, x to the 12th. Square root of x. Exponential. Like e to the x. Like 2 to the x, like 5 to the x.
It's a constant too.
It's always, right, what we know, power rule, so power rule says like derivative of x to the n is n times x to the n minus 1. The exponential rule says the derivative of a to the x is a to the x times the natural log of a. In this case, n is the constant, the power is the constant. In this case, the base is the constant. Over here, neither one. You can't use power rule, you can't use the exponential rule. However, you can get tricky. Legal algebra is always allowed in the house. Start with y equals x to the x and take the natural log on both sides. First of all, most important question, is this legal?
Yes.
Right? Natural log perverts. It sounds like perverts. The natural log preserves equality. Why the natural log?
You can't
Why
bring
would
down the n.
anybody, Carmen, why would you ever think to use the natural log here? You could p in front of the log, also not a thing to say. In college, they'll laugh at you. Natural log of y is x times the natural log of x. Now what?
You can divide the natural log of x.
Now we're all laughing at you. You cannot divide by the natural.
No. Divide the natural log of x. Because then it's, never mind.
You absolutely cannot do that. Of all the things that you're allowed to do in this world, that's not one of them. You can't divide by natural log because it's natural log of stuff. How about take the derivative? Do we know how to take the derivative of natural log of y? With respect to x? Do we know how to take the derivative of x times natural log of x with respect to x? Okay, let's do the right-hand side. Derivative on the right. I'm going to do 1 times the natural log of x plus x times 1 over x, a little product rule. Derivative on the left. Be careful. We're doing a derivative with respect to x. X is the variable here. So the derivative of natural log of y is 1 over y.
dy.
Times dy dx. What we just did, and it's been a while, this is implicit differentiation. And so now that you've just done your implicit differentiation, your goal is to solve for dy dx. Okay, so dy dx is the natural log of x plus x times 1 over x. Everybody get this is 1 times y. But what's y?
It's up there.
Y is just x to the x power. This is the derivative, oh, sorry. Here. X to the x. This whole process that we just did is called logarithmic differentiation. It's a technique that you're going to use when your base is a variable and at the same time the exponent is a variable. You're like taking the two of these things and mushing them together. Okay. Can I be your tutor? I probably will be. I'll share my fee structure later. Okay, anyway, that is it for our proving derivatives. We could have done a whole lot more. Tomorrow I'll be the guy with the air horn screen.